This lecture covers how to do the chi-square test in R. If you look at iLearn under course modules, you're going to need this data set. We're going to use it. And this is the R code. So we'll download those. That's the PowerPoint if you want it. That's probably just going to open it right up in R. Yep. Okay. So most of the statistical tests we've done so far are based on the idea of the normal distribution. And we assume that data are normally distributed, at least the numbers, and then we use attributes of the normal distribution to help us make inferences. There are a whole lot of other kinds of statistics that don't rely on the normal distribution. We call these non-parametric statistics. Some of them are distribution free. There's a whole lot of them. I'm just going to focus on the chi-square test today. It's based on the chi-square distribution. We talk about it in this class because it's a widely used tool to determine statistical significance of categorical variables. So you use this if you have one column of data and it's a categorical variable. It lets you know, do you have the same number of observations in each category? That's basically what a chi-squared test is. So this symbol here is the chi-squared. So the way you calculate your chi-squared is you take the sum of the observed value minus the expected value squared divided by the expected value. You sum those up, and then that becomes your chi-squared. I'll show you this example. So let's say we did a survey, and we asked people, are you in favor of school vouchers? And 23 say yes, and 17 say maybe, and 50 say no, I'm against that, for a total of 90 people. And you want to know, are there the same number of people in each of these categories? Is support for school vouchers balanced across categories? Well, that's what you do with this test, right? So you have a degrees of freedom, which is the number of categories minus 1. So 1, 2, 3 categories minus 1 would be 2. So 2 degrees of freedom. Our null hypothesis is that we have the same proportion of individuals in each cell, or that this number is the same as this number is the same as this number. Now, I can look at that and see that that's not true, but this is what a chi-square test tells you. The alternative is that they're not all equal to each other. You choose your level of risk. We'll do 0.05. The test statistic is going to be the chi-square. Then we'll compute our test statistic and compare it to the critical value. The critical value for a chi-square is right here would be our degrees of freedom, and then we just go 0.05, right? So we have 2 degrees of freedom at 0.05, so that gives us 5.99. So whatever I get for a chi-squared value, I compare it to 5.99. If my value is bigger than 5.99, I reject the null hypothesis, and I conclude that the values are not all equal to each other. So here's how you do it, kind of by hand, just to help it make sense, right? You say, well, what's the expected frequency? Well, things have frozen up for me for some reason. We'll restart that program. I don't know why it closed on us. So if the values were all exactly the same, to figure out the expected value, I just take the total divided by the number of categories, right? So if there's 90 total, for them to all be equal, this would have to be 30, 30, and 30. That's your expected value, right? It's like, if they were all equal, what would that value be? Well, it would be 30, 30, and 30. So I take my observed 23 minus 30, which would be 7. I don't know why I put a negative there. Oh, because it is negative. 23 minus 30 is negative 7. I square that, I get 49. 17 minus 30, negative 13. 50 minus 30, 20. I square each of those, right? Then I divide these each by 30. Then I add them up, and I get 20.59. So this is bigger than 5.99. So I reject the null hypothesis and I say, nope, those are not all equal to each other. Like this is the chi-square test. It's used regularly when people put tables together and show you how many observations are in each table. They'll say, look, chi-squared statistically significant. But you just have to decide if it makes any sense to you, like if there's a reason you should think these should all be equal to each other, right? If there's not a reason to hypothesize that they should all be equal to each other, then perhaps the chi-square test isn't the appropriate test for you to do. But that's how you do it. So to do it in R, super easy. I'll just show you how to do it. So we're going to read in that data set. I'm going to call it D2. It's called chi-squared data. So I have, so I'm just going to clear everything and read it in again. So here I have 90 observations of one variable, right? I've got people that are for, I got people that are maybe, and then people that are against. Okay. So the first thing I have to do is make a table of that variable to put it into this format. If I just try to do a chi-square test, I'll show you. If I go chi-squared test of D2 $voucher, I'll get an error message because there are no numbers for R to use. So you have to create the table so that R can run the chi-squared test. Right? You can't do observed minus expected if you don't have any observed values. So the table gives R the observed values it needs. So the first thing you do is you make the table, and then you do a chi-square test of the table, and then you get the output. So here again, same chi-squared value, same degrees of freedom. Here's my p-value, right? So bigger than 5.99, less than 0.05. I reject the null hypothesis. Okay. So there's this Duncan data set. Here's how I would get the Duncan data set if I were you, and I didn't have it already. I would go library car, like that. When I read in the car library, then the Duncan data set's in that, so I can just go D1 equals Duncan. Maybe I have to put in quotes, let's see. No, that's not what I wanted. D1 equals Duncan. There we go. So in this data set, I've got professional, I've got their income, right, prestige. So I've got the type, right, professional, white collar. So that's the Duncan data set. So it tells you if the job, here's the list of jobs right here. And then it tells you if it's blue collar, white collar, or professional. And I want to know, is there the same number of blue collar jobs and white collar jobs? Are there the same number of those? Right, so the first thing you would do is, first I'll let you go ahead and do it, right? Because I just showed you how to do it. So now you can go ahead and pause, because you won't learn anything if you just watch me do it. So first I make a table of type. And then I do, so D1 $ type. There's my values. There's my chi-squared. There's my p-value. Okay, so ready to answer my questions. What is your null? That the proportion of blue collar equals the proportion of white collar equals the proportion of professional. Just going to go back and show you the table. Right, 21, 18, and 6. So my null hypothesis is that these values all equal each other. The alternative is that they do not all equal each other. We use the chi-square test. Critical value is 5.99. Our test statistic was 8.4. And what do you do with the null? You reject the null hypothesis. We could do this with other variables. In this, sorry, I'm going to go back to here. Let's see if the attribution recode data set is here at chi-squared. It is not. It's probably here in data sets. Right there is the attribution recode data set. I'll move it up so that it's easy for you to find. So in this data set, you've got how often people read the news, right? And you see there's a missing value there. And then you have a couple times, right? So we could do a test to see like if these all have the same values in them. But remember what I showed you with the ANOVA, how missing categories mess these things up. So you have to get rid of the missing values and then get rid of that category. Otherwise, it'll mess up your statistical test. So again, NA omit. So my data set this time was called D3. So I'm going to call it D3 again, and it's going to be get rid of all the missing values of D3. Then now that that's 0, I got to get rid of that category. So I use drop levels, and then I get where it's just 6 categories. Right, on the chi-square test, if you have those blank categories, it'll ruin your degrees of freedom calculation, and it'll ruin your chi-squared calculation. So I'll show you this in the code, how to do it. Just kind of run through it real fast. So call it D3, read in attribution recode. There it is, 1,800 observations. Get rid of those down to 1576. Drop the levels. Option SciPen gets rid of scientific notation. And now if I do that table of news frequency, then I see, okay, I've got the 6 categories. Then I run the chi-squared test of that. And then I see, wow, that chi-squared is much bigger than whatever the critical value would have been. P-value is less than 0.00. So there are not the same number of people in each of those categories. Party ID, actually, I think this is on your homework, right? There's the same number of people in each of these categories. Again, you can look at it and see that they're different, but the chi-squared will do a hypothesis test. So I could run that code, right? But the null is that they're all equal to each other. The alternative is that the proportions are different. I will use the chi-squared test. My critical value is 5.99. That can't be right. Let's go here. Back to this critical value thing. If I have 6 categories, it's 11.070 is my critical. Oh wait, no, that one had 3, sorry. So that would be 5.99. This one would be, there we go, okay. 5.99, my chi-squared on the party ID is 49.874. That is larger than 5.99. My p-value is less than 0.05. So I reject the null hypothesis. So you can't really statistically do a test to see which group is different. You just look at the data and you can see, right? Like, I don't need to do a statistical test. I mean, the statistical test tells me that they're different, but I can see, oh, more independents than Republicans, more Democrats than Republicans. I can see like very few people never watch the news. Most people regularly watch the news or several times a week, at least in that survey. So that's the chi-squared test. Hopefully it feels like a little bit of a break after some of the other stuff. It's going to start getting dicey after this, so be ready. It'll be, we'll do a review of all these tests we've done so far, then we'll get into regression, and then that gets us through to the end of the semester. So good luck, everybody. I hope you love it.